By Yuval Filmus about degree D polynomials.
So thanks for the invitation, and thanks for those of you who stuck around to the very last talk. There's a spoiler. At the end of the talk, we will all clap for the organizers of this workshop, but you'll have to wait for 15 minutes or so. Maybe an hour. Yeah, so which degree D polynomials are close to Boolean? So really, to state the question, I will need to explain what do I mean by degree D polynomials and what do I mean by close to Boolean. So we'll start with some more classical stuff, and then we'll do less classical stuff. Okay, so I guess the first result, maybe in analysis of Boolean functions, is the KKL theorem, I think, historically. Like if you look at the earliest, is that true? But then the second result is this Friedrich-Laino theorem from 2002, which originally it was Friedrich-Laino has this quantitative version of Arrow's theorem, and there was a question about if you're almost satisfied the constraints of Arrow's theorem, then what does your social choice function look like? Anyway, so there was some actual motivation behind this. So here's the FKN theorem. Okay, so if f is degree 1 of f from 0, 1 again to the reals is a degree 1 function, and it is close to Boolean in the following sense. Okay, then f is order epsilon close to a constant or a dictator. Okay, so what's going on here? So we have a function. The input is n bits in 0, 1, and the output is a real number. It's degree 1. This means that you can express it as a degree 1 polynomial in the inputs. Okay. And it's close to Boolean in an L2 sense. This means that if you look at each point, you look at the squared distance from 0 or 1, like the one which is closest, and you take expectation that you get something small. Yeah, so which functions satisfies this? So if epsilon is equal to 0, so your function is Boolean on all points, then we have the 0 function, the 1 function, the xi, and 1 minus xi. Okay, and what this FKN theorem states is that even if you're just close to Boolean in this L2 sense, then still the only way that you can accomplish this is by being close to one of these Boolean degree 1 functions. Okay, so this is considered by some to be a fundamental theorem in this area. Others, like there's somebody here who I mentioned the FKN theorem, and they said, what is this? So apparently for the newcomers, it's no longer necessary. Yeah, the original proof used hyperconductivity, but actually in Guy's thesis, there's an inductive proof. And also the paper had a mistake, which Guy pointed out and corrected. So yeah, and now we'll see Guy's name again. Okay, so the degree D generalization. This is the Kindler Safra theorem. Okay, so this is Guy and this is Muli Safra. So just the same thing for degree D. So if f function from 0, 1 to the n to the real numbers is a degree D function, and f is epsilon close to Boolean. Okay, epsilon close to Boolean just means what I wrote here, so I'm not going to copy it again. Okay, then f is order epsilon close to a Boolean degree D function. Okay, so we don't really have a nice list of these functions for D larger than 2. For D equals 2, we can do it, but in general, but what you can say is that the only way to be close to Boolean is if you're actually close to one of these Boolean degree D functions, and in particular, you're close to a junta. So you really secretly you depend only on a small number of variables. How small? We have here improved some parameters. Is how small? Yeah, so you won't find this theorem listed in the paper for two reasons. One reason is that there is no paper. Okay, there are some drafts available on the author's websites. They're not the same. There is a published but not a refereed version in Guy's thesis. Okay. There is now a published version in this paper of Keller and Klein. So if you want to cite it and you want an actual paper, then you can actually do it now. And I also have many proofs on my website. Yeah, and it's also not stated this way, but it's still true. Okay.
This is the roast of Guy, then I would like to speak next.
I would say it should be interpreted as the roast of Moody, but just my opinion. Yeah. Okay, so this gives one answer to this which degree D polynomials are close to Boolean. Maybe nobody asked, but I'm taking an expectation over x. So what is the distribution of x?
Distribution of x?
Yeah.
I asked. There you go.
Yeah. What's the distribution of x?
Uniform.
Uniform, yeah. So, but it makes a big difference. So what we're going to do in the rest of the talk, we're going to discuss two different distributions on the inputs. Okay. So the rest of this talk. Okay, so we're going to discuss two domains. So the first domain is the P bias cube, which I'm going to go over what this means in a bit. And the other one is the symmetric group. And we're going to ask this question for these two domains, and we're going to get some answers. Not all of them, but some of them. Okay. Now, I should say that, yeah, as will transpire, this is really about the structure of functions. So I think it's a good fit for the theme of this workshop and this semester. Yeah, so what is the P bias cube and why do we care about it? So the P bias cube is, we still have n inputs. But now whenever we say that something is close to something else, oh yeah, I didn't say, but this is also in an L2 sense. Also, I didn't say it here. So f is order epsilon close to a function means that the expectation of f of x minus g of x squared is order epsilon, where g is a constant or a dictator. Yeah, so in all these expectations, we can, instead of considering the uniform distribution, we can consider this P bias distribution, where every point is equal to 1 with probability P. So this is a distribution mu P. So mu P of x is P to the sum I xi, and is 1 minus P to the sum I 1 minus xi. Okay, so this corresponds exactly to this Erdős-Renyi random graph, for example. Yeah, so you put in each edge with probability P, it's the same thing, only now we don't have a graph. It's just unstructured input. So this is kind of an important distribution. Like, let's say one of the most celebrated results outside of this area proper is the Friedguth's threshold theorem, or Brueggen's appendix, or Hammond's theorem, whatever. So there are a bunch of them. And this is exactly in this setting, where we think of P as small. So if P is constant, then all of these results, that they still hold. Yeah, maybe you have to change the proof, but like it's essentially the same thing. Or maybe there's also even a reduction, this Nathan Keller business. But when P is small, then we see phenomena that we don't see for constant P. So for example, this sharp threshold business, when P is not small, then the corresponding structure is a junta, and when P is small, then it's a lot more elaborate. And that's what we're going to see here as well. Okay, so this is the P bias cube. What is a symmetric group? We all know it's the group of all permutations of n elements. But here's how I want to think about it. So a symmetric group is a set of all n by n permutation matrices. So we have these n squared or n by n array of inputs, which I call xij. Each of them is 0, 1. There's exactly 1, 1 in every row and column. And this also gives you a definition of degree. So a function is degree d if you can write it as a degree t polynomial. Okay, and then you can ask the same questions and hope maybe for an enlightening answer. Okay. So the first thing we're going to start with is with the p-biased FKN theorem. So this will be the FKN theorem for short. And this is a good opportunity to mention that Gil Kalai prefers his name read this way, but even Israelis don't do it. So if you say Kalai, it's fine. But yeah, so people have a right to choose how they pronounce their name. Yeah. So here's the statement of the p-biased, or rather the beginning of the statement of the p-biased FKN theorem. So it will be the p-biased FKN theorem. So we let p be at most a half. If p is more than a half, then let's just switch zeros and ones, not a big deal. If f, go on to the end, mu p, r has degree 1 and is epsilon close to Boolean, then f or 1 minus f is order epsilon close to what? Yes, I already gave you some of the answer because like I'm doing f or 1 minus f, but let's not worry about it. Yeah, so maybe the first guess would be that you have to be close to the same thing as here, to a constant or a dictator. And this is kind of true, but also kind of false. And we'll see in a moment in what sense it's true and in what sense it's less true. Yeah, so are there other functions other than these constants or dictators that are also close to Boolean, linear functions? Maybe somebody can think of a function like this.
So if p is 1 by n, can you take or?
Yeah, for example, p is 1 by n. So I'm not taking or because or is not degree 1, but you can take a sum. Yeah. So that's a very good observation. So here's the suggestion. We take xi1 plus xin, where okay, so when p is equal to 1 over n, then yeah, we can do it. We can just take sum over everything, but when p is 1/2, then we're only summing over one thing. Okay, so what's the difference? How does this thing behave? What is the distribution of this, roughly? So each of them is just a Bernoulli p random variable, and we're summing m of them.
Poisson.
Yeah, so it's roughly Poisson MP. Then what's the probability that the Poisson MP is not 0 or 1? That's a trick question. Okay, what's the probability that the Poisson random variable is equal to 0? Okay, so Some people here are experts in statistics, so they should know this. So like e to the minus mp is roughly 1 minus mp. It's equal to 1 with probability mp times e to the minus mp, which is roughly mp, and it's equal to 2 with probability mp squared over 2 to the minus mp, which is roughly mp squared over 2. And yeah, so as we take higher and higher numbers, then we get even less and less probability. So the probability that we're not Boolean is roughly mp squared. Okay, so this means that we need mp to be at most what? If you want to be epsilon close to Boolean?
Square root epsilon.
Square epsilon, yeah. Okay, where m is at most 1 or m is at most square root epsilon over p. Okay, we just did the calculation. Yeah, we didn't really do it all the end because so this will work for like L0 and we need L2. Let's not worry about these things. They work out. Yeah, so this is a theorem, and it has an interesting corollary. Okay, so f is order square root epsilon goes to a constant or a dictator. And order square root epsilon plus p close to a constant. I hope you can still see. If not, then well, I just said it. Yeah, so that's why I said that this guess is both true and false. So it is true that if even when p is small, then you're still close to a constant or a dictator, but you're not epsilon close, you're only square root epsilon close. Yeah, so in many, many applications, we don't really care. Right? Epsilon, square root epsilon is the same thing, even like something which is like inverse tower is good enough for us. But maybe from a structural perspective, we do care. And then when we look at it with this magnifying glass of up to order epsilon error, then you get this more refined structure. And you can also say, so if I think of p as small, then maybe this thing is like very small. And it really says that the only way that a function like this can be close to Boolean is if it's essentially a constant. Okay, so kind of the question is not so interesting because like the function is 0. Yeah, so I'm describing the class of functions which are essentially 0. Yeah, but I don't know of any direct proof of this. I mean, maybe there is, but okay, so this is the p-biased FKM theorem. And what we're going to do next is we're going to look at the symmetric group and see what happens there. This will be slightly more interesting, but it will be very similar. Yeah.
For the symmetric group, if you just look at the slice of specific language, everything goes through.
Yeah, so actually these papers are originally written for the slice. But now we know, thanks to work of Noam, that the right way to look at the slice is use this coupling with the p-bias cube. This works unless like the slice, the weight is very, very, very small. So if your weight is not like super small and not a constant or anything, then there's no reason to think about the slice at all, because you can just apply this coupling and you get the same result that you get for the p-bias cube with p, which is the weight over n. Yeah, but if you insist, you can also do it directly on the slice.
P-bias the Safra.
Yeah, we'll get to that. That will be the third thing. But maybe the most interesting here. So you have to keep the suspense. Okay, so yeah, let's erase this. Okay, any more questions about this? So now for the symmetrical, this is really kind of a question that is more related to the previous workshop.
Sorry, what happened to the degree D?
Yeah, I was saying that we'll do degree D later.
Oh, we're doing that later.
So, yeah. This is actually the main topic of this talk, is degree D. But first, we do the symmetry.
Can you say something about that, please?
Yeah, I'll say in the end because the proofs are all the same. But I can say something now. It's just a reduction to the unbiased case. This is essentially the entire proof. And hopefully there will be time to tell you how you do it, like what the reduction looks like. And maybe you can also do it somewhere directly using global hyperconnectivity, but I suspect that if you do it directly, then you won't get epsilon. You have to so many words. We haven't tried. So FKN theorem for Sn. But before that, maybe we should ask ourselves what happens if epsilon is 0. So if we have just a Boolean degree 1 function. So there's a theorem of David Ellis, good, and Van Pilpel. Yeah, Pilpel in Hebrew it means peppercorn. It's a really stupid name. It's not the original name. So one of these names that they changed when they came to Israel to be more patriotic or something. Not something called something else. So not to put the Han down. So if f from Sn to 0, 1 has degree 1, then f is a dictator. So I haven't said anything because I didn't say what the dictator is. You can define a dictator as the same as a Boolean degree 1 function. Yeah, so what can you do? Which functions are exactly degree 1? Exactly Boolean. And people don't know. Yeah. Right, exactly. So, so there are two forms. Either you do something like this, xi j1 plus xi jm, or you do xi1j plus ximj. Or pictorially, if this is a permutation, then either you're summing something along the same row or something along the same column. Okay, yeah, this is proved using the Birkhoff polytope. Okay, so now and you can guess what the FKN theorem will say. So we'll start with the corollary. So this is a corollary of the theorem. B. If f from Sn to R has degree 1 and is epsilon close to Boolean, then it is order square root epsilon close to a dictator. So maybe, yeah, it's striking. It's really the same thing. So like if in the case of the pre-biased cube, you could say, oh, because this question is not interesting because like you're close to 0. In this case, you're close to a dictator. So it can actually be close to many different functions. So it's not a vacuous statement. Right. But you can also, if you care about this, you can look at the structure up to an error of order epsilon. And here, like, there's some historical background. So 10 years ago, I can't remember, we had some papers with David Ellis and Ehud Friedgut about this question, and we got some partial results. And then we all forgot about it, and now suddenly this came up again, and yeah, so now we have the optimal answer that you'll see in a moment, but somehow the other people don't care as much now. So they moved on. But I'm still telling it to you. Maybe you will care more. Yeah, so and the structure is going to be the same as here. So we're going to sum these xij's. And now the question is, here the condition is that you're not summing too many of them. So what is the corresponding condition for permutations? So this will be the actual theorem. So it's under the same conditions. F or 1 minus f is order epsilon close to a sum of xij's where, so here there will be some constraints. Okay, so what are the constraints? So we can try to do the same calculation that we did here. Okay, so let me erase this. Is it pink? Yeah, so we have like xi1, j1 plus xim, jm. And we want this thing to be non-Boolean with probability epsilon. Okay, so let's try to estimate what's the probability that this thing is non-Boolean. So for this to be non-Boolean, we need to have two of these summands which evaluate to 1 at the same time. Okay, so we will say that xij, xi bar, j bar are a conflicting pair. Maybe not the best terminology. If I is different from I bar and j is different from j bar.
Conflicting.
Yeah, so yeah, maybe it's not the best terminology, but well, that's what's in the paper, so it's too late now. So it's conflicting if they can both occur together. You can think maybe it should be exactly the opposite, right? But I think it's conflicting because it makes them non-Boolean. Yeah, we'll have a different name for it for the Kindler-Safra theorem. So, okay, so your probability of being non-Boolean with most like number of conflicting pairs over n minus 1. This is a probability of hitting both of these xij and xi bar, j bar. Yeah, so we want this thing to be at most epsilon. So we want to have there are order epsilon n squared conflicting pairs. And there's another technical condition that will be only few of these xij's. They're only order n many. And moreover, all such functions are order epsilon close to Boolean. Okay, so again, so in this setting, you're going to be either f or 1 minus f is going to be close to a sum of these xij's, so sum of coordinates, sum of not too many of them. So for a dictator, we need at most n, or at most n minus 1. So here I promise you at most order n. And there are not so many conflicting pairs. So this is this back of the envelope calculation. Okay, so this is the structure that I promise you. And it so happens that if you have a function that is of this form, then it's also order epsilon close to Boolean. So in this sense, the structure is tight. Yeah.
Some order n in the same solution. Right?
Yeah, it's like something a bit technical. So this is related to spreadness, globalness, all of these properties. So yeah, I tried to find this example that shows that if you don't assume that, then this is false, and like the calculation didn't work out. But kind of what's happening is, so if you had many different different things, then maybe like things will add up, and you will still be at distance epsilon in L0 from Boolean, but maybe the relative distance will be bad. Yeah. Yeah, that's also possible. So you're saying we got it for free. Yeah. So that's also possible. But we'll need this anyway for the Kindler Safra theorem, so it's good to put it here explicitly. But yeah, you might be right. Yeah. Yeah, but this point that I was making, so here we have an upper bound. So if you have where it goes. So if you have only a small number of conflicting pairs, then you will be close to Boolean. But really your distance to Boolean is, you can reverse this. This is like an approximate equality up to constant factors. This is something we call the reverse union bound, and it kind of like some kind of proxy of sunflower business. Yeah. Anyway. Yeah, and now what's the point of having this structure? So we can prove the corollary. So I don't know if how to prove the corollary directly. Okay, so this structure is useful for something at least. Yeah, for the proof, I might have more time to say about it later, but it's a reduction to the Boolean cube. So it's the same proof. It's a bit more technical, but it's the same basic idea. Questions?
Does the same result hold if you consider functions not to 0, 1, but some finite set?
Probably, yeah. So I mean, the proof will need some work, but morally it should be true. So yeah. So definitely this Safra theorem for the p-by setting and this degree D generalization, they work in this general setting. I mean, it's not formatted like this, but it was in some earlier version. Here, yeah, probably, but it will require some effort. Yeah, and even like the epsilon equals 0 case, like it's not so clear what exactly you'll get, but yeah.
For permutations, it's not necessarily natural to consider 0, 1.
Right. Yeah, also I should mention in the paper there are also results for L1 distance, not L1, L infinity, L0. There are many questions we can consider, and it's a bit something for your students to do. Yeah, but this is a good point, and the other papers that definitely do work in this more general setting. Yeah. Here there might be some issues. Yeah, more questions. Yeah.
So where are these functions used from SL to 0, 1?
Yeah, so okay, so the reason that we thought about this 10 years ago is because of intersecting families of permutations. This would be one way of proving stability. Even back then, there was a different, better way, and now there are even better ways using the junta method. So that's where these questions came from. But you can think of this as trying to generalize the study of the Boolean cube to other settings. Yeah, it's true that I can't necessarily motivate these particular results, like they don't have any immediate or any applications. But you could say that this is, a natural question, a natural thing to study, the things that we say.
That's why this application is to stability results.
Yeah, but I think by now we know how to prove it in some other ways, and also back then you could prove better results without using it. So it was a fake application to begin with, but Yeah, it's a good question. Like, how do you choose the topics that you work on? That's a good answer. For maybe for another time.
No, but for the triangle intersecting, Kindler Safra was the only way to get stability.
Okay, sure. This is for the unbiased setting. Yeah. Okay, so there might be some actual differences. Yeah, but the frame of mind is we know some stuff on the Boolean cube, and we sometimes care about functions on other domains. Let's say for my grant application, I wrote the Grassman scheme, TTP conjecture, high dimensional expanders, maybe little PCPs. Like you can make the case. Not necessarily for these results, but for some results. And like this is a lot of stuff that Norm and Corsair have been doing is exactly this, like not these results, but some other results. This is a very fruitful avenue. So yeah, I don't think it's pointless. These particular theorems don't have any application for them. Yeah. Now for the thing that we asked. So the final part will be the degree D case of this. So this would be the key biased in the Safra theorem. Maybe one thing I should say, this constant here doesn't depend on P. And this is an entire point. It's a global constant. And it will be the same thing here. If you can depend on P, then this proof is just the same as the unbiased case. Only interesting if it's independent. So let P be at most a half. Let F 0, 1 to the n mu P reals the degree D function, which is epsilon close to Boolean. So degree D function just means that you can write it as a degree D polynomial. Okay, then F is order epsilon close to a function G such that. So now we will have 4 conditions. So G has degree D. G has degree D. Okay, I'm writing it as 0 because this is kind of the point here. Okay, G of y is in 0, 1 if y is at most D. G is sparse junta, so this I'll define. And G has order epsilon over P to the E minimal non-Boolean inputs of weight E, which is also something I will define. Okay. And moreover, such functions are order epsilon close to Boolean. Okay, and the corollary, F is order epsilon to the AD, 1 over AD, close to Boolean degree D function, and order epsilon to the 1 over VD plus P close to constant. And this number, BD, we have a formula for it. It is probably the same as BD, but I couldn't prove it, so yeah. Okay, so now what we'll do is I'll explain to you what is this sparse junta business. Like in hindsight, this is like just spreadness essentially, and I'll explain what is this minimal non-Boolean input. Then we'll see how it corresponds, like what happens when d equals 1, why it's the same as the previous results. And then hopefully I'll have maybe a few minutes to talk about the proof. Yeah.
Condition 3 is for every, for some E.
Yeah, so it's for all E, but it turns out that the minimum non-Boolean input has bounded weights. So it doesn't matter. They haven't defined it yet, so you can imagine what it means. Okay, so maybe let me start with the first condition. So what does this tell us? Sorry, this, condition number 1. So if we look at the expansion of G as a polynomial in the Y's, it tells us that we know what are all the possible coefficients. Okay, so let's take as an example the degree 1 case. So in the degree 1 case, with d equal to 1. So condition 1, so let's say that G is C plus some I C I Y I. So what does condition 1 say? So G of 0 is just C. So this has to be 0, 1. Let's say C equal to 0. And now G of EI, this is the unit vector with only a single 1. This is equal to C plus CI, which is CI, which is 0, 1. Yeah, so we get that G is a sum, or 1 minus the sum. Okay, and in general, like we will get all the possible coefficients, and we get what we call a quantized polynomial, because the coefficients, they come from some finite set. Okay. Now, what is this? Let's do 3 first. So a minimal non-Boolean input is just an input of the functions, which is, well, the function is not Boolean for this input, but if you replace a 1 by 0, then it is Boolean. Okay, so Y is a minimal non-Boolean input if G of Y is not in 0, 1. But G of Z is in 0, 1 for all Z that are below Y. Okay, I'll give an example. So when D is equal to 1, then we have essentially one type of non-Boolean input. So this would be G of EI plus EJ, or EI plus EJ, when CI and CJ are equal to 1. Okay, so this gives us, this is some sort of forbidden configuration. It's not really forbidden because we allow a bit of it. But let's say here, so here we said that there was a bound in the number of n's, and here there was a bound in the number of conflicting pairs. And this corresponds to some kind of bad configuration that cannot occur too much. And this bad configuration is a minimal non-Boolean input. Like here, it was just a conflicting pair, so this is, yeah, this is we define it as a minimal non-Boolean input. And here it says that like xi1 and xi2, or rather ei1 plus ei2, for example, this will be a minimal non-Boolean input of this function. And we can't have too many of them, and that's the reason that M is bounded. And the reason that we get this is because otherwise the function wouldn't be epsilon close to Boolean. Yeah, so a minimal non-Boolean input is some input on which the function is not Boolean, but it's minimal. Like, yeah, it's very, well, I don't know if I can say it in any other way.
The bounded for 3 assuming that P is much less than E.
E.
And suppose that some E of them are all equal to 1.
No, I think it's fine this way. Okay, and now I have to define 2. So we look at the support of G. Okay, what's the support of G? This is the set of S such that the coefficient of this monomial is non-zero. Yeah.
You went to 2.
Yeah, that's what I wanted. I want to explain what is a sparse junta.
I know. Explain to me, I still understand.
Okay, yeah. Yeah.
So since you're counting how many minimums and digits you have for P variables, now you have monomials, right? Or you don't have it.
So this function G is a polynomial, and a non-Boolean input. It's just an input where the function is not Boolean, and it's minimal if whenever you switch one to 0, then it suddenly becomes Boolean. Okay, so as an example, in this case, in this function,
Epsilon of P, you mean a fraction out of all possible inputs of P.
no, you just go over all possible, not fraction, just sum over all possible, over all inputs which are minimal and Boolean. Let's see what happens here. Okay, so how many non-Boolean inputs do we have here? So what's the non-Boolean, minimal non-Boolean input here? It's Eij plus Eik. Yeah, so here, this. Yeah, so sorry for the mess. So if G is that's y1 plus ym, then a non-Boolean input, a minimal. Y is a minimal non-Boolean input. And only if y is of the form ei plus ej, where I and j are in between 1 and m and different. Okay, so this is an input at which the function is equal to 2. But if you go down, then you get 0 or 1. So it's Boolean. Okay, so how many inputs do we have? So the number of these inputs is m choose 2. Yeah, so I'm saying that m choose 2 needs to be at most epsilon over p squared. Okay, now either m is equal to 0 or 1. And otherwise, m choose 2 is like m squared. And then m squared is at most epsilon over p squared. So m is at most squared epsilon over p. And this is also exactly the same thing that we had for the, yeah, I just erased it, for the symmetric group. So p to the power e. Sorry. Yeah, it's right here. So it's the same thing as here. So a conflicting pair is exactly the same thing as a minimal non-Boolean input. And okay, now we're good with this. Okay, so the support of G is the set of S such that the coefficient of this monomial is non-zero. So we want support of G. We think of it as a hypergraph. So support of G as order 1 over p to the e edges of weight e, and the same holds for all lengths. Okay, if you don't know what a link is, and I just spell it out in the case d equals 2. So for d equals 2, so we have all 1 over p non-zero ci's and order 1 over p squared non-zerocij's. So this will be the coefficient of yi, yj. And for each I, order 1 over p non-zero cij's. Yeah, so this is essentially the spreadness condition, globalness, whatever you want to call it. We called it, you use some other term. But, and this we get for free from the proof, and it's necessary to reverse some unit bound somewhere. like this. Yeah. But let's not worry too much about that. This is this condition, we see it here. Okay, so in the interest of time, let me spend like a few minutes answering Avishai's question. How do we prove this? Because this will be very easy. And then we'll open for other questions. So I'm sorry we're a bit in a rush, just because somebody actually asked. So I'm going to outline the proof of the theorem about the p-bias cube, but the proof for the symmetric group is similar, maybe slightly more interesting. So our starting point is a function f, which is from 0, 1 to the n mu p to r, where p is at most a half. Now, for every s, fs is the restriction f to 0, 1 to the s obtained by substituting zeros for the other coordinates. Okay, so now if s is chosen according to mu 2p, and y is chosen according to mu half of 0, 1 to the s, then y is chosen according the same thing as choosing y according to mu p. This is the main observation. It's not very deep. Yeah, so one way to sample something according to the p-bias distribution is first to sample something according to the 2p bias distribution, and then to sample it according to the 1/2 distribution. So p is 2p times half. This is the deep observation here. Yeah, so on average, fs is close to Boolean. Okay, and then we just apply the FKN theorem or the Kindler-Safra theorem on these fs's. And we somehow paste all these things together. We do this using, in the FKN theorem, it's very easy. And in the Kindler-Safra case, we do it using agreement theorems, but there's also a way of not doing it this way. Let's not worry about it. Okay, so we get by design that g, so g is the function we obtain by pasting, yeah, maybe I should say. And so to some gs, where gs is the function that is promised to us by the FKN theorem or the Kindler-Safra theorem. And we paste all of these gs's to this global function g somehow. Okay, so by design, g is degree d. This we essentially get because the function gs are Boolean. Okay, this we get because of the way we do the pasting. And this we get because the function is epsilon close to Boolean.
G is actually equal to GS on the system, or is almost.
Oh, you need to do some. So what you actually can do is you do majority decoding. So for every coefficient, you look at all the GSs and what all the relevant GSs and what value they give to that coefficient, and you choose the plurality, and this will work. So this is the proof. For symmetric groups, we need to use a different process. So we choose two random permutations alpha and beta. And then we look at all the permutations that either map this to this and this to this, or they map this to this and this to this. And then the same for the next pair and so on. Okay, so this gives us a copy of 0, 1 to the lower n over 2. And now we apply this FKN theorem and it's the same thing. So I said it in like a few words, but It's a similar idea. Yeah, open questions. Do this degree D case for the symmetric group. And maybe a more exciting open question is do this in Q analogs, like Grassmann scheme, bilinear scheme, where I think Doe has some partial results. But we don't even know how to do the epsilon equals 0 case for these other domains. So we kind of none of the techniques work. And one reason is all of these proofs, they reduce to the Boolean cube. And if you cannot do it, then we don't know what to do. We don't have any other technique except for global hyperconductivity, which is, I guess, what Doe is doing. Yeah. So I guess I'm already over time, so I'll end here.
For 0, you have some results on like the slides here.
Yeah, so there's another funny result. So yeah, where the degree D functions on the cube are juntas, but this is not the case for slices if the weight is very, very small. So you can take the function like this here, and take the function x1 xd plus xd plus 1 x2d plus. Okay, and if you're working on the slice and choose k, where k is less than 2d, then this will be Boolean, but not a function. Okay, and I can tell that this 2D is optimal. So if it's at least 2D, then you will get a function. And also answering your question, this gets a lot more interesting if the alphabet is not 0, 1, then there is still a formula. So this is one case where you cannot do this. You cannot compare it to the pre-bias cube, just because P is too small.
Other questions? Matt, let's thank Yuval again.
I want to take this opportunity to thank the organizers and